Yeah. Okay. Here we go. Okay. 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 Hi, everyone. We are going to Hi guys. After okay, so got echo. This is my white space board that I'm going to be using. So I'm going to try and write on this so that you can kind of see, and I'll try and make sure that everybody can see what I'm writing when I'm doing examples and stuff like that. You should be able to kind of select which screen you're seeing the biggest. I am going to probably, I am recording this session. More so it'll be my talking or the document camera feed that's coming through. And I'm going to post that on Canvas. So as soon as everything is finished up and it finalizes the video for me, I will get that posted in Canvas. So if there's something you didn't catch, or for anybody who wasn't able to join this session, they can go in and view it on there. And I'm going to try, I did one of these with my stats class last night, and I discovered that on my part, whatever main screen I have is what gets recorded. So right now it's recording me, but I am going to probably switch over to my white screen here in just a little bit, and use this kind of like the display screen, and then I'm just going to basically be talking on top of it. I do ask that if you've got questions, put them in chat over here on the side, and as they come up, I will try to answer them, especially if they're regards to the current thing that we're talking about. If not, I'll loop back and answer any sort of the questions that do come up. I want to give everybody the opportunity. Oh, there's lots of y'all. I did also open this up so that this is both of my algebra classes in one session, so that I wasn't having to like tandem do the same lessons over for each side. And I'm going to try and get all this lovely lighting situation fixed up. It's great fun trying to do all this lovely lighting. So that is where we're going to go. Like I said, I'm pretty much going to kind of just do a quick run through of the sections 3.1 through 3.3. And then I am going to do the example stuff in the document camera side so that you can kind of see what's going on. And I'll talk through any of that information. Basically, this was the best way that I could come up with to make this work without just trying to have y'all completely dependent on the videos, because there may be something where I say it slightly differently or something like that, and you may prefer how I say it, you may prefer how the other videos say it. I'm just trying to put options out there for everybody to where they can have what works best for them inside of all of this. So I'm going to go ahead for me and switch so that this is now the main thing that's focused on. So starting in section 3.1, we're going back into quadratics, and we are discussing we're discussing quadratics. This is more so from the graphing side of stuff, and then the application side, as opposed to the solving stuff. Now, we're still going to do some stuff in the solving side. So we'll see some of that stuff coming back from section like 1.5 as far as the solving goes. But this is kind of leaning more into the graphing style of stuff. So we start off with the parabola shapes. Okay, so parabolas are either right side up or upside down. This is our parabola shape. And every parabola has an axis of symmetry that cuts it in half. Where the axis of symmetry and the parabola intersect is called the vertex. Okay, so in either one of these. Now, one of the things that will stay consistent with this is if A is positive, then the parabola is going to open up like this. If A is negative, then the parabola is going to open down in this shape. And regardless of whether or not, we've got two forms that we're going to see used. Regardless of either form, if A is positive, it opens up. If A is negative, then it opens down. Okay, so that's pretty consistent. Now, the first format, or the first form that we discuss, okay, is going to be this A x minus h squared plus k. Now, this should look familiar from when we did circles, okay? This is going to be your right and left movement, and it's going to do the opposite of what you think it's supposed to do. So if you have x plus 3, then it moved to the left 3 spots. Okay. Now, what is going to be a little bit different is this part is your up and down, but there's not a set of parentheses around it. So this is going to move exactly the way you think it's supposed to. So if you see plus 4, it's up 4. If you see minus 2, it's down 2. Okay. Okay. Now then, and again, if A is positive up here, it opens right side up, like a U-shaped. If it's A is negative, then it opens upside down. Now then, when we get into the graphing stuff, and every parabola, regardless of its format, every parabola starts its life with its vertex at the origin. So when we talk about the graphing stuff, and I've got the steps listed in the PowerPoints, which y'all have access to on Canvas, okay? The first thing we're looking for is does it open up or down? And this is just so that we have the concept already in our head of, if I'm supposed to be opening in a right side up parabola, I should not be seeing dots that look like this. If I say it opens up, my dots should not be forming something that opens downward, okay? So that is really more just a mental thing. Then we want to get our vertex. So we want to figure out, how does it move left, right, up, down, that kind of thing. X-intercepts, we're going to set the whole equation equal to 0, and we're going to solve it. This is going to feel kind of like when we did inverses, where we're kind of peeling layers back off. The y-intercepts we're going to plug in, and then we're going to plot and graph. Plotting technically is just putting dots on a graph. Graphing is the actual connecting the dots to make a shape. So the example that I've got in the PowerPoint that we will discuss is going to be this one. Let me try and straighten my stuff out just a little bit. My rigged up document camera here. Okay, so kind of going through those 5 steps. Oh, that's off screen. Move over. Okay, so whether this opens up or down, we see negative up here in the front. So this says that this is going to open down. Now, I'm going to try and do this over here. Hopefully we'll be able to kind of keep track of some stuff. So this is going to be my grid space that I'm going to work with. Now, second thing that we need to do is we need to figure out the vertex. Now, from this, we know that -1 is the opposite. Normally we think minus is to the left. So this actually goes right 1 unit. And the +4 is our up and down. It does exactly what we think it should. So this is going to be up 4. So down here on my grid space, I'm going to go right 1 and up 4. And there's going to be my vertex. Okay. Now, the third thing was our x-intercepts. And in order to do that, we're going to set our equation equal to 0. And we're going to solve this. So first thing I'm going to do is subtract 4. Next thing is, I can't deal with the squared yet. I want to get rid of this negative. So I'm going to divide by -1. Okay. Now I'm going to get rid of squared. So I'm going to do square root. And again, if we bring in square root, we need to bring in the plus and the minus when we come out of this. So this is going to be plus and -2. Down just a little bit. So we're going to have 2 equals x minus 1 and -2 equals x minus 1. We'll add 1. I'll move that up here in just a second. Okay, so I have x-intercepts at -1. Put that one there. And at 3. Okay, now, one of the things to note here, okay, kind of bringing this back to what we talked about on the first one, is we talked about that axis of symmetry goes through the vertex. So I can draw in that axis of symmetry. Now, what should happen? Because it's an axis of symmetry, that is our fold in half. Everything should mirror match, okay? So if I notice from this axis of symmetry, this dot is 2 spots over from or to the left of that axis of symmetry. This dot is 2 spots to the right. So they are mirror matching on the x-axis, that they are that far apart. Now, I'm going to move up here to do my y-intercept. And for y-intercept, sorry, it's a little hard to get up there. We're plugging in 0. So -1 squared is going to be 1, and then I still have a -1 on top of that, plus 4, and that's going to give me 3. Now, there's that dot. Now, technically, okay, I have another dot that I can put on here without doing any math whatsoever. I can mirror match this point onto the other side of the graph. So if I notice, this is 1 space to the left of our axis of symmetry. So if I go 1 space to the right of our axis of symmetry, and I'm going to put it in, and I did this in an asterisk, just so that you know that it is, I didn't do any math behind this. It is just an additional point that I have. Then we're going to play connect the dots. Now, the only thing about parabolas is do make sure they're nice and pretty rounded through that vertex. A lot of times, students want to make them kind of sharp corner points, and they are not a sharp corner point when this happens. So now we have our nice pretty graph. Now, on MathLab, when you try to go in and do the graphing stuff, and I realized that my Wednesday night class, some of y'all saw this instruction before we left for spring break. My Monday night, this is kind of your first time seeing this. On MathLab, when you go in, they have a parabola tool, okay? And I think you have to put in 3 points. I think it's 3 points. Generally, you want to make sure that you're doing at least 1 point on each side, okay? So that you've got 1 on one side and 1 on the other of that vertex. If you can put the vertex in, that's a great spot to have as well. But it will connect kind of the same way that you had the circle tool. It has some stuff built in that it knows how to build these parabolas. If you give it so many points, it can build them through as they're processing that, okay? So hopefully you kind of get the idea of what we're doing with that format. And again, that form is called standard form, okay? So then moving into the other format, okay? The other format that we have is general form, and we've had general form before, okay? This is our ax squared. Having fun trying to learn how to document camera. Ax squared plus bx. Again, if a is positive, this is going to open up. If a is negative, it's going to open down. They are consistent with that. They don't switch it up and say, oh, we're in a different format, we're going to do a different rule. Nope, it's the same rules both times. Now then, with this one, what everybody always kind of weirds out about, okay, is when we talk about the vertex, the notation looks like this, okay? And everybody weirds out. Guys, B is going to be a number. A is going to be a number. This whole thing is going to be a number. All this is take this number and shove it in that equation and get an answer. Okay, so this is going to come out to be a number. This is plug the number in and get an answer. Okay, so don't like weird out, freak out when they do that. Okay, Now, as far as the rules or the order that we do for this, it's the same as the other one. We want to start with, does it open up or down? The next thing is we want to find the vertex using this. Now, x-intercepts, we're still setting it equal to 0. But this is where you may have to use a quadratic formula or factoring or something like that to find those values. Y-intercept, the y-intercept math is super nice and pretty for this one, okay? When we have these. So, and then we're going to plot and graph. So again, I'm going to do the example that's in our PowerPoint. Okay, I'm trying to stick to stuff that everybody has access to. So I'm going to write this one up. So we're going to do. No. Okay, so this is our equation. So again, I want to figure out whether or not it's going to be up or down. So again, I see a negative up here in the front, so this is down. Okay. Now, second thing is our vertex. So we're going to do negative b over 2a. So b is 4 over 2, and our a is negative 1. This will be negative 4 over negative 2, which is 2. Okay. And then we're going to plug that in. So 2 squared is going to be 4. So I'm going to have negative 4 plus 8 plus 1. Negative 4 plus 8 is 4 plus 1 is 5. So our vertex is at 2, 5. So again, I'm going to kind of build our grid space down here. 1, 2, 1, 2, 3, 4, 5. So there's the starter. Now, next one, okay, and I realize that for some, and I'll move this back up when I come back to the graph, several times in class, yes, this is still section 3.1. So with this one, guys, just again with the experience that I've had, in order to get this 1, the only way you can get stuff to multiply to be 1 is 1s, and there's no way to make 1s make 4. So quadratic formula is now going to become our best bet. So we're going to do negative b plus or minus square root b squared minus 4ac all over 2a. So we've got negative 4, 16 plus 4 over negative 2. Now, normally, okay, we would sit here and go, oh, let me clean up the square root of 20 or whatever it is. Now, if I'm going to have to go to a graph, this is where we want to go into decimal stuff, okay? So this is going to be negative 4. Square root of 20 is roughly 4.47. Okay, and then we'll do negative 4 plus the 4.47 and negative 2, and then divide by negative 2, and then also the minus 1. And with these, we get negative 0.235 and 4.235. Okay, I'm going to try and move this over just a little bit. Now, as best I can, 0.235 is kind of like a quarter. So I'm going to go at roughly a negative 1/4 and then 4 1/4. It's kind of hard to do because I've got really fat markers. And then, so now this still has, okay, that same, we've got that axis symmetry running through. This one, it's a little bit harder to see because this is not an even spacing. This is 1, 2, and about a quarter to the left. This is 1, 2, and about a quarter to the right. But because those x-intercepts are not as clean and pretty as the ones that we saw in the last one, and it's not to say that they're always going to be ugly spots when they're in this format. There are pretty ones that come out of this format, and there are ugly ones that come out of the other one. They don't always, but it still holds that that's what's going to happen. Now, for our y-intercept, and I'm going to do this up here in this little bitty space, the math for this is really simple. Sorry, a little too high. Guys, this is going to be 0, 0, and 1. So my y-intercept is at 1. And again, you can do the mirror match. This is a little bit cleaner point, so it's a little bit easier to mirror match. This is 2 spaces to the left of the axis line. If you wanted to, you could put in that other dot over there on that other side to keep that one nice and clean and pretty. Again, plane connect the dots. And again, try and keep it round through that vertex. Okay. We've got that as our parabola. So hopefully that kind of makes. Now, the next thing that we're going to look at that comes up in this section is they are going to bring up and combine this idea of the vertex format for a general equation that negative b over 2a format for the part of the vertex and the maxes and mins. They're also going to do the same thing that we saw over in, I think it was section 2.1, either 1.8 or 2.1. It was one of the early sections where we talked about what is the maximum and where does it happen, where they split those two things up, okay? So now then, there is one edit that I need to make on the PowerPoint, okay? On the PowerPoint, and I'm going to pull my PowerPoint up here. Bleak. Okay. Okay, good. This first statement is correct, okay? The second statement on this one, this symbol right here, okay, this greater than symbol that I have right there, sorry, this symbol needs to be a less than symbol, okay? So on this slide, if you have the PowerPoints, okay, the first statement is correct, okay? If A is positive, that is going to be a right side up parabola. You are going to have a minimum for that one. The second one is, it should say if A is less than 0, that means A is negative, then you are going to have a maximum, okay? So again, this is about 9 slides in or so into that PowerPoint if you're looking at it. So that is an edit that needs to happen in that PowerPoint if you've got your PowerPoint, okay? If that is what you're looking at on your PowerPoint. Now, again, what happens with this is they're separating it, okay? So what we've got going on here is a maximum. They're saying this is the max value, and this is where it happens, okay? So they're doing that same split that we saw them do back over in one of those earlier sections of maximum value where it happens, okay, when they're going through. Now then, the next example that it talks about, okay, and this one, everybody wants to overthink this one, okay? They give us the equation, okay, and they ask, does this have, without graphing it, okay, so they don't want us to put it on a calculator, they don't want us to graph it, map it, anything like that. They want us to decide, will this have a maximum or a minimum? They don't even ask me what the maximum is, they just want me to decide whether or not it has a maximum or a minimum. Guys, all I have to focus on is that first thing. That first value is positive. If it's positive, that graph opens up, which means I have a minimum. That's all that question asks. So if you're looking on the PowerPoint and you see this and it asks, decide whether or not it has a minimum or a maximum value, all I have to look at is the first value. It's positive. That means it opens right side up. I now am guaranteed I will have this minimum value. That's it. That's all it's asking to be done with that. Okay. The kind of last thing that has to happen in this section is the application stuff. Okay. And I do have my lovely little timer running here so that I can make sure that I'm watching my time. Hopefully they're going to pop up like they did last night and tell me I don't have a 40-minute cut limit. The next one is applications. Now, when we're talking about application stuff, okay, awesome. There are mostly two things that you're looking for. One is vertex, because they will often say something along the lines of, what is the maximum or what is the minimum? When they say that they're looking for a maximum or a minimum, those always happen at the vertex, okay? The other thing that they sometimes look at is x-intercepts. So one of the examples we're going to look at is a football being punted, okay? And so we talk about, you know, here's our field and they kick the football. One of the things that they're going to ask about is this vertex spot up here. They're going to want to know, how high did the ball go? When did it happen? Where did it happen? Something like that. The other thing is they're going to want to know, when did it hit the ground? Back over here, okay? We see this same application. Sometimes they are launching a rocket. Sometimes they're throwing a ball up in the air. They're chunking something, whatever, and it's going up and coming down. And so they're worried about the high spot, and they're worried about when it's going to hit the ground down here again. Now, the other thing that we have to watch out for is, what are they measuring in? Okay, what do the variables represent when they're doing this stuff? Okay, as far as, because sometimes they'll do things in measurements that we're not traditionally thinking of. Like, I may be normally used to things being measured in miles and they're doing things in kilometers, or I'm used to things being in inches and they're doing it in feet, or vice versa. So that can sometimes lead to answers that seem really big or really small by comparison to what they're supposed to be. So we'll see. I think I've got one example that does something kind of like that. So looking at the first one, they ask us to find minimum product of two integers whose difference is 10. Okay, so this is the one that they ask us to do. Now, the big thing here is making sure that we kind of have our equation. So first off, when we talk about product, that means multiplication. Okay, so I'm going to set up P for product, and then we know it's multiplication. So I'm going to pick two letters, X and Y. So they're being multiplied together. Now, the other thing that we have going on is difference. And we know that difference is subtraction. So they're telling us that if I subtract my two numbers, I get 10. Now, the concern that we have right now is I've got two equations. I also have way too many letters going on here, okay? So what we're going to do is we're going to solve the second equation for one of our letters. So what I'm going to do is I'm going to add the y back over to the other side so that I have x by itself. Okay, so now x is by itself. And then what I'm going to do is I'm going to replace this x right here with this quantity over here. Since we're saying x is this amount, this x can be replaced by this. So now I've got kind of trying to do some stuff in color here so you can kind of see. Now then, if I multiply this out, and then I'm going to put it in order, or in the traditional order. Let me preface that. So y squared is positive, so I'm leaving it positive. The 10y is also positive, so I'm leaving it in positive. Guys, this is a quadratic. If they want me to do a minimum, then I need to know my vertex. So I'm now going to do negative b over 2a. It's going to be negative 10 over 2. Okay, so it's going to be now. Okay, that is one of your integers. Okay, so out of the two that I'm trying to find, this is one of them. Now, from here, you can do two things. One, you can try and figure out what integers are 10 away, okay, from this. Or you can go ahead and plug this in. I'm sorry. Okay, when you plug this in, this answer that we get back out is the minimum product. So now I can ask myself, negative 5 times what gives me negative 25? And my answer is 5. So my two integers, and sometimes they'll ask us a couple of different parts. One is if they want the minimum product, it's the negative 25. Okay. If they ask for what are the integers, like they ask us to do, it's going to be the negative 5 and positive 5. And sure enough, if you think about those are 10 apart on a number line. So they meet the qualifications for having a difference of 10 for this one. Now, the nice part about this is if you have a problem like this where they change it up and they do what is the minimum product of two integers whose difference is 12. This is your skeleton, okay? Everywhere I have a 10, you would put a 12. Your numbers will come out slightly differently, but this is your basic framework for how that is going to get processed and moved through, okay? So hopefully everybody's good with that. Now, next one is the one about the fence. Now, this one was always a little strange to me. I don't know why you would buy your fencing first and then decide, I wonder how big of a pen I can make. I always figured out how big a pen I wanted first and then what amount of fencing I needed. But, you know, maybe I'm just weird. Okay? I'm going to try and figure out how to move all this stuff. Okay, so here's what we know. Besides the fact that my phone is all sorts of wonky job. Okay, I have 120 feet of fence. And we are doing a rectangular, okay, we're doing a rectangular pen. And they want us to figure out the dimensions that are going to work. Now, with this one, I am like, it's a geometry problem. Okay, so I'm going to start by drawing myself a lovely little picture. Okay, so here's my rectangle pen. Now then, I'm just going to label that. So I've got, I'm going to call it X and X and Y and Y. So the idea here is I can have a really long, not very tall fence and use all 120 feet of fence. I might have it be like 59 feet long by 1 foot tall. That's not going to get me a whole lot of area in the middle, okay? And as I make it kind of shorter side to side, it's going to get a little bit taller, which means I am gaining. But at some point in time, if I keep shrinking it this away, I'm going to wind up with a really narrow but really tall fence, which is the exact same problem, okay? Instead of having a fence that looks like this, I wind up with a fence that looks like this. they're the same pin, they're just oriented differently, okay? So there's got to be a happy medium somewhere in the middle. Now, when we talk about rectangles, there are two main equations that we need to know. One is we know we're dealing with area. Now, area on a rectangle, length times width, base times height, depending upon how you're taught. In this case, it's going to be x times y. That looks familiar, okay? The other one that we know is perimeter, okay? And so for perimeter, we know that that's adding all the way around. I've got an x and another x and a y and another y. So I have 2x plus 2y. Now, the other thing we know, though, is I do know what my perimeter is going to be. I'm using all 120 feet of fence. So now we've got an equation that looks like this. Guys, this hopefully looks very, very similar to the last one, okay, that we saw. I'm going to want to solve this second equation for a letter. I'm going to solve for x again. And I'll switch colors here real quick. So I'm going to do 120. I'm going to subtract the 2y. Okay. And I'm switching colors here just for contrast. Okay. Just so that you can see the difference here. And then we're going to divide by 2. Now, the 120 divided by 2 is going to be 60. 2 divided by 2 is going to be y. And that gives me my x. And again, I'm now going to replace this up into that other equation. So I'm going to write this down and then I'll move it. Okay. Okay. Distributing. Okay. Now, if you're going to get this into your traditional order, watch yourself on your signs. Okay. Let's see if I can get my camera to refocus. There it goes. The y squared is negative, so I need to make sure that it maintains that negative. And the 60y is positive, so I need to make sure that I maintain that as well, okay? So now, negative b over 2a. Okay, now, that's y. This is where I am such a visual person, okay? Going back up here to my picture. That number is now 30. If that side is 30, that side's 30, okay? I have now used up, between just those two sides, 60 feet of my fencing, okay? So I've used up 60 feet to handle those two sides. Guys, out of the 120 feet that I have, there's 60 feet left. Those 60 feet have to also be split evenly between the top and the bottom edges that I have. So this must also be 30 and 30, okay? So again, the two sides was 60 feet. Okay? See if it'll focus a little bit for me there in just a second. Okay, and then I divided that into those other two sides. Now, you could still plug in the 30, okay? So back working on this other 30. If I plug that in, and guys, from this, I could figure out 30 by 30 is 900. Sorry, I know that's kind of up there in that corner. Guys, I can figure out that the area of this pin is 900 square feet, that it's a square, okay? You could also plug in move this over so you can see the mouth. Okay, guys, you could plug this into that equation, and that's your max area. This is one of those scenarios where, personally, it's a whole lot easier for me to go back to the geometry idea for this than it is for me to run it in and go, okay, My maximum area is 900. 30 times what gives me 900, and try to figure that out, kind of that in that backwards direction. The question came up, wouldn't it make it a square, not a rectangle? Yes. Squares, though, are rectangles. Okay, so in order to be a rectangle, all you have to have is opposite sides are parallel and 4 right angles. Technically, a square hits those qualifications. Opposite sides are parallel, and we have 4 right angles. Squares have the extra additional add-on of all 4 sides are the same. So every square is a rectangle, but not every rectangle is a square. Okay, so that's one of those little geometry things. There's also some ones about rhombuses and kites and some other stuff, where one is the other one every single time. Now, there is a second kind of subgroup that is done of this problem. Okay, I'm going to get rid of this problem, okay, and show you the setup that they will sometimes do. Sorry, I'm not trying to make anybody motion sick here. Okay, the other version of this that I have seen them do is that they build the pin against some sort of a natural 4th side barrier. Okay, so this is a building, this is a canyon wall, this is a river, this is a something where they're only going to use the fencing on 3 sides. Now, with that being done, and it doesn't really matter what your letterings are that you're using, you would have something that instead of the perimeter being 2x and 2y, this would be x and 2y. So that slightly changes the problem. It slightly switches up. It doesn't change how the problem is solved. It just changes what that equation is going to look like. And in this case, I would probably solve for this singleton letter. I realize it's the same x that we did on the other one, because all I would need to do is pull the 2y back over to the other side where the number was, and then I could plug straight in. We wouldn't have the divide by 2 that we had in the last one, okay? So this is another style of that same kind of area problem that I've seen done. Now, the last one in this section is the punted football one. Okay. So this is the equation that they give us. It is an upside down parabola because we have the negative out here in the front. This is one of those instances. Now, the x that's getting plugged in here is how far away we are from the kicker. Okay, so how far down the field. And then the answer that would come out would be how high the football is. Sometimes these are done where the x represents time. It represents like how many seconds have passed by. So just make sure that you're watching. This is again where when you're getting into the application problems, be careful about what the format is or what they're discussing on it, okay? So the first thing it asks is, what is the maximum height of the punt of the football? So they want maximum, and they ask, where does it happen? Come on. Come on, camera. Catch up. Okay. Let's try. So negative b over 2a okay? And this is feet from kicker, okay? So that's the x part. Plugging that in, Okay, so this is where we plugged it in. And guys, I literally have this side written, so please don't think that I was doing all that math in my head. I wasn't, I promise. Okay, I literally have stuff. See, look, all of my stuff written down for me. Okay, so I'm not that good. Okay, I will claim it other times, but not now. So this is the highest that football got. Okay, so 36.81 feet, almost 37 feet up in the air. And then it happened 59 feet from the kicker. Okay, and again, that was just an application of us finding our maximum. And again, with them doing this as that negative b over 2a, that was that. Now, the second part of this is if it's not blocked by any defensive player, how far down the field will it go before it hits the ground? Okay, so this is that other part of the problem where they want to know kind of ground. Now, because this is, I'm thinking about our shape, okay, they're looking for this spot down here. Now, with the setup that they have for this, since the answer values represent how high the ball is, y'all, the ground is at 0. Okay, so what we're going to do is we're going to set this equation equal to 0. Now, this is a scenario where I am not going to factor this bugger. I'm not doing anything. This is going straight into a quadratic formula. Okay, there is no reason for me to do otherwise, so we're just going to go straight in. So negative b squared minus 4ac all over 2a. And again, y'all, I'm going to move over here. Now, all of this through here has been like the exact decimals. This one is a rounded decimal, okay? This goes a lot farther. It goes a lot farther. Now, again, do be careful with this. Make sure that you're doing the negative plus this, get an answer, and then do the division, and then do the subtract, and then the division. Now, the two answers that I'm getting, okay, now, you may be looking at this and going, well, how can I get a negative? Okay, well, let me help out here, okay? Sorry, needs to have his leg up, kick, ball, smiley face, arms, okay? What's going on here is in the math world, we don't know that this is an actual problem. All we have is an equation. This is if I could track the ball to before it came out of the kicker. So keep in mind that we're doing, this is a punted football. When our football players punt a football, it's not on the ground, okay? It's in their hands. They either have it dropped low or they drop the ball and then kick it. So the ball is not on the ground when it is being kicked, okay? It's not like a kickoff when they're doing that. So this negative 1.67 would be if we could track the ball kind of back before, okay? The main one that we would be concerned with is this 119.67. Now, first thing that in my mind happened is, what the heck? A football field is only 100 yards, okay? Again, though, this was being measured in feet, not yards, okay? So when we think about that, 100 yards on a football field is 300 feet, okay? So this is now definitely within the realm of possibility. This is really close to, if you do the conversions over, it's about 40 yards, okay? Which kind of makes sense for how far it would be on a putted thing down the field. But this is where I was saying be mindful of the units, because when I first did this problem, kind of working through it, I was going, wait a minute, 120, that's going to be like, we should have this guy's like, yeah, we're gonna punt it away on the 1 yard line and he can field goal the sucker. I mean, like, come on now. It's done in feet though. Okay, so this is again that instance where you got to watch your units, because sometimes those can be like, wow, I must not be right in my answer. No, it's perfectly correct. It's just not in the units that we would say be used to. Okay, so we're going to now move into the next section, into 3.2. 3.2 is a little bit faster. The examples in this section are not as involved when we're doing this. Now, what's going to happen with this section is we're basically trying to do some graph sketching. It's like taking a picture with an old school, like, manual focus camera, okay? The ones where you actually have to click in to get a little bit of focus, okay? We are never going to have a perfect picture for what's going on here, okay? We're just going to have bits and parts that are correct as we're processing through. And so when this happens, there's going to be a little bit of stuff that's always up in the air. I will be using kind of multiple colors to kind of help tell us what we do know that's guaranteed versus what we don't know, or kind of what's up in the air, okay? So the first thing is when they talk about a polynomial function, okay? Everybody always freaks out when they see this notation, okay? This whole little like subscripted thing. Guys, they just didn't want to run out of letters of the alphabet. That's it. Okay, so instead of doing A, B, C, D, okay, guys, you can't use the letter I because that's the imaginary thing. You can't use the letter X out in front. You're not going to use the letter Y. What happens if you run out of letters? Okay, so instead of doing that, they just put this little subscript on it, okay? Now, this biggest power, okay, whatever this biggest power, that is the degree, okay? So if you have something like x to the 5th plus 2x squared, that is your degree. So this would be a 5th degree polynomial. Okay, so it's just the biggest power that's on there, okay? And then this piece right here is called the leading coefficient because it leads the bunch, okay? I told y'all we're real creative namers here, okay? So leading coefficient, biggest power. Now, what we're now going to talk about is getting the idea of what happens at the edges of my graph, okay? Now, first thing that we need to talk about, though, is smooth continuous. Now, it is a whole lot easier for me to show you a smooth and a not smooth graph, okay, than it is for me to try and explain it. This is smooth. This is not, okay? So smooth means nice, humpy, bumpy, lumpy, okay? Snake-like curves, no sharp corners, okay? Sharp corners, bad. Now, the other thing that it talks about is continuous and not continuous. So again, I'm going to do, here is continuous. That's not continuous. The idea here is continuous is connected, okay? So you can think of continuous is connected. If you have to pick your pencil up to finish the drawing, okay, you cannot start on one side and trace through, but you have to pick your pencil up. It is not a continuous graph. So we want smooth, continuous graphs when we do this, okay? So nice, humpy, bumpy, lumpy, connected graphs, okay? Now, the next thing is what they call end behavior when they do this, okay? When they do end behavior for this stuff, there's this lovely chart table thing and whatever, and it's wonderful, it's lovely, it's gorgeous, but everybody always loses track of it, okay? So here's what you need to know. If your degree, okay, it's either going to be even or it's going to be odd, okay? Here's what's going to happen. If it is even, it is going to act like a parabola, okay? Meaning both ends are going to be up or both ends are going to be down, okay? If it is odd, it's going to act like a line, which means either it's going to have this direction or it's going to do this. Now, with this, we do oftentimes turn them a little bit, so that it's either going to be this pair, okay, this end down, this end up, or it's going to look like this pair, where this end is up. And guys, the concept here is that there would be like some graph stuff connecting what's going on in between here, okay? We don't know kind of this greenish part, but we do kind of know what the purple stuff is. So this is what the chart is talking about when it talks about that end behavior. Now, when we look at, you know, what's going on or how this is going to be applied, okay? What's going to happen here, okay, is look at something like x to the 4th minus 4x squared. Okay, so here's my biggest power. It's an even number, which means it's going to act like a parabola. Now, when we think back to the stuff that we just did in section 3.1, okay, if this is positive in the front, then it's going to open up, okay? If it's negative, then it's going to open down. So since this is positive, both ends are going to be up. Now, I have no clue. This may do like this. It may do something like that. It may just do something like that. I don't know what's going on in this bottom part, okay? I don't know if it's this kind of really humpy, bumpy, lumpy one, if it's got some humpy, bumpy, lumpies, or if it's really just simple. But I do know this kind of hot pink red color that's up here at the top. I know that's what the ends of my graph do, okay? If this had been a negative in the front, then I would have had both ends down, okay? Again, not knowing what's going on in the middle of my graph. And we're going to be stacking and layering this stuff in as we go, okay? So this is just going to be one of the things that we do. So now, looking at another one. Okay, so again, biggest power here, okay? This one is odd. So this is going to act like a line. So when we talk about a line, we think about slope of a line, okay? So now looking at, we have a negative out here in the front. A negative line had a slope that went like this, okay? Now, when we talk about this in graph shape, we're going to slightly turn, okay? But we're keeping that negative slope. This end is going to be up and this end is going to be down. Again, I don't know. This may be something super simple. It may be something that's got lots of humpy, bumpy, lumpies. It may do something like that. I don't know. I don't know what's going on, but what I do know is what these two end values are going to do. I do know what those shapes are going to look like. Okay. This end is going to be up, that end's going to be down. Okay. Now, the next thing that this talks about is the zeros of a polynomial. Now, the zeros are where we hit the x-axis. Okay. Now then, when we talk about zeros and where we hit on the x-axis, okay, what can happen with these graphs is they can either, and I'm just going to show one direction here, cross over the x-axis, meaning they start on one side and they move to the other, okay, and this could go the other way too, depending on which way it needs to go, or they can do what's called touch and turn, which basically says they come into, hit this point, and then come back out. Again, this could also come up from the bottom if it needed to. The way that we tell this is what's called multiplicity. Okay, with the multiplicity, if it is odd multiplicity, then it's a crossover point. If it's an even multiplicity, then it is one of these touch and turns. Now, the other thing that's going to happen, okay, is the higher the multiplicity, the flatter this graph wants to get, okay? So for example, this might have a multiplicity of 1, but this is a multiplicity of 3. This would be a multiplicity of 2, and this would be 4. Now, I'm going to explain where this multiplicity, how you know what the multiplicity is, okay? Like how you identify it in the equations and in the setups, okay? And then we'll see how this all works. Now, this concept combined with kind of where the graph starts and ends, that end behavior, this end up, that end down, is going to help us start to get an idea of our pictures and our shapes, okay? So we're going to look at we're going to look at this equation. Okay. Now, this is a 4-termer. We're going to go back to our factoring by grouping. So I'm going to pull these two. So x squared, that's going to leave an x plus 2. I can pull a minus 4, and leaves me an x plus 2. Again, we see that this factor matches. I'm going to pull it to the front. Okay. That's going to miss this. Now then, setting each piece equal to 0. Okay, now what I now have is -2, 2, and -2. Now, my zeros are -2 and 2. But because -2 is here twice, oh, where did my stuff go? Sorry. Hang on. Yes. No. Okay. Okay. Sorry, let me get my ID back up here. I lost my ID. Let me see. Where is... Okay. Whee. Okay. Okay. Sorry, y'all. I am having loads of fun with this. Okay, there we go. Okay, so because -2 is here twice, this has a multiplicity of 2. So if we were going to start the idea of what this graph is going to look like, and I'm going to move up here, okay? Okay. First off, biggest power is a 3, so this is going to act like a line, okay? And it's positive. So positive slope line goes this way, okay? Hopefully y'all can see my writing stuff again? Yes? No? Okay, good. Okay, sorry. Yeah, somehow like my phone went weird, okay? So positive slope, okay, kind of keeping that idea of a positively sloped line, this end up, that end down. We have -2 and +2, okay? These are based on the zeros that we found down here below all of this work, okay? Now, that multiplicity 2, okay? We said, let me move this, okay? So we said -2 had a multiplicity 2. If you remember, that means this is a touch and turn. So coming back up here to our graph, okay? If we think about this graph is going to have to come up from this point. This is at -2. This is a touch and turn. So this must go this away, okay, for it to touch turn. It's going to have to come up because I don't touch the x-axis anywhere else, okay? The other one at 2, okay, coming back down here, 2 was only here one time. So its multiplicity is 1. It's an odd number. So this thing's going to have to come down here and turn around someplace down in the bottom and then come back up. And so this is going to be a crossover point, okay? Note how this fits in with the rest of the picture. There's no way I could have been down here and the graph finish up there without me crossing over, okay? There's no way that I could have crossed this over without if I had stayed down here in the bottom of my graph. So that's how the graph, knowing these ends, helps me start to do the little bit. Now, how the rest of this looks, I don't know. This may do something really simple like this, okay? It may do something a little more complex and involved where it's got some other humpy, bumpy, lumpy things in it. I don't know. But the pink stuff is what we do know, and that is guaranteed, okay? So now then, looking at the next one, okay, and I'm not necessarily going to graph this one all the way through, but if they give you something like, sorry, this is your multiplicity, okay? Which means that's also your multiplicity. So when you set these up, when I do x plus a half equals 0, this is my 0 at -1/2. Its multiplicity is 2, which means that is a touch and turn, okay? When I do this other one, this is my 0 is at 5, but its multiplicity is 3. So this means it is a crossover, but it's also going to have that little bit that is a little bit flattened, okay? So if we were going to talk about picture-wise, here's 1. So there's -1/2. Okay, and there's the one at 5. Now then, if, guys, kind of talking through this, if we did this piece squared, we would have x squared with a bunch of stuff behind it. This one's going to give us an x cubed with a bunch of stuff behind it. When you put those together, your leading term is going to look something like -4x to the 5th. So it's an odd power. So again, it's a line, but it's a negative line. So this end is up, this end is down. we talked about this being a touch turn. If we're coming from here, this touch turn must happen this way, okay? Again, we've got to get over to here with the cross, so this is going to come up and round out somehow. This is going to have to round out someplace up here. And then this is, instead of coming straight down through here, we're going to let it flatten just a little bit, okay? And again, this would now play connect with the other pieces. With this up end here, you can move it over a little bit if you need to make it fit in line a little bit better. But this is the concept of what you've got, okay? The next thing that's going to happen in here is what they call the intermediate value theorem. Intermediate value theorem is really, really wordy, that says if you have a positive answer and another x gives a negative answer, you hit 0 in between, okay? Picture-wise, the easiest way to do this is, here's an X and Y axis. Here is something that has a negative answer. Here is another something that has a positive answer. Somewhere between here and here, you have to hit the x-axis, because there's no way you play connect the dots from here to here without hitting that purple gap someplace, okay? Now, you may hit it once, you may hit it 14 times. I don't know. It may be, sorry, straight over. This may be that we hit it 3 times, okay? But I'm guaranteed to hit it at least 1 time, okay? Because you can't go from here to here. Now, you could also have, guys, if this one was up here and that one was down there, I could hit it this way, okay? But you have to hit it between these 2 spots on the x-axis. What this does is it helps narrow down where we're doing like a search field of stuff, okay? The other thing that this slide talks about is turning points. Turning points is the number of hilltops or valley bottoms, okay? This is called a turn, okay? And what you're allowed to have is n minus 1. Now, you don't have to use them all. So if you're allowed to have 5, but you only use 3, that's fine. But you can't have more than what they allow, okay? So when we're talking about, okay, an example for this, okay, they ask us to show that there's something between -3 and -2. If we plug in -3, it's going to be and then if we plug in -2, okay, we go from -42 to 5. That means somewhere between, on our x-axis, okay, so we've got, this one is way down here, this one's up here. Somewhere between -3 and -2, in that little gap right there, I have to hit the x-axis, okay? It has to happen someplace in there. Now then, as far as the method, okay, the order that I use for graphing a polynomial is slightly different than the books. Okay, I'm going to bring this into play here real quick. Okay, I always start with the leading coefficient test, which end up, which end down. When that happens, then I do the x-intercepts, so where I hit the x-axis, and their multiplicity, whether it's a touch turn or a crossover point, and am I going to have any flattening of stuff out. Then I'm going to find the y-intercept. I'm going to plug in 0 and find it. Symmetry is way down at the bottom of my list, okay? Some books put symmetry way up at the top end. I do not, okay? I just don't think that you have too many graphs that it's not necessarily going to happen. So I kind of rank it a little bit lower. And then turning points, always err to the side of use as few turning points as you can, knowing that it can be embellished more rather than putting in a bunch of turns and a bunch of humpy bumpy lumpies that may or may not be there, okay? So we're going to look at one of these from top to bottom so that you can kind of see what's going on. So I've got 2x squared, or sorry, x plus 2 squared, and then x minus 3. Okay, so starting with kind of our end behavior. Okay, if we multiply this part out, we're going to get x squared with a bunch of stuff behind it, times this is going to give me an x cubed. So the front of this thing is going to be 2x cubed with a bunch of junk out behind it. So using the fact that my biggest power is 3, that's odd. So it's going to act like a line. So again, I'll get my grid space going kind of down here. Try to move all this together. So it is odd. So it's going to act like a line. And it's a positively sloped line. So this thing should be going kind of up this direction. Okay. So we're going to have up on this side, down on that side, kind of working that through. Now, for my intercepts, this one they did really nice, y'all. It's already pre-factored for me. So we're going to do x plus 2 and set it equal to 0. And this one has multiplicity of 2, again, because of that power. So this is a touch turn. And then for the other one, this one only has a multiplicity of 1 because it doesn't have a power up there, which means it's an automatic 1. It's just there the single time, which means this is a crossover point. So now coming back down here, here's my one at -2. Here's the one at 3. And again, using my graph to help me out, if this is going to come up from here, the one at -2 is a touch turn. So this must do this way. This thing's going to come back around and have to curve somewhere down through here and then cross over here. Okay. Now, there is no symmetry to this. And the reason that I know this, when we talked about symmetry, we talked about it being even symmetry, which means it folds in half on that y-axis. Guys, if this is over here at -2 and that one's over there at 3, it is not going to have symmetry, okay? It's also, this lovely little bugger is not going to rotate 180 degrees and do that type of symmetry either. Now, as far as turns, you take your biggest power, which is 3, so I'm allowed to have 2 turns, okay? And that's the most that I'm allowed to have. Now, guys, one of those is right there. That touch turn that I had to use on the 0, that is one of my turns. So now, what does the rest of this look like? Okay. Oh, I left something out. Y-intercept. This is going to be -24. Okay. I'm going to mark that right there is -24. Okay. So this is one option. Maybe that other touch turn is down there through that intercept. Now, another option may be that this thing comes down a little bit further and then crosses up through the rest of that, okay? That part we don't know. They don't ask us to know that information either, okay? This is a spot where all we have to have is a basic idea. And like I said, the pink parts of this, okay? So the end behavior, the x-intercepts, what happens at those, and that y-intercept, that's all we really have to know, okay? If we are looking at making a graph picture happen, okay? So there is that one. Now, the good news is section 3.3 is even shorter than either of the other two, because I know we are pushing about an hour and a half almost into this, okay? And I appreciate, again, I am going to upload this video onto Canvas when this is all said and done, okay? We're going to try and get through this last one fairly quickly. This is going to be some lead up stuff that we're going to be using going into next week. So the first thing is doing long division. Now, if you remember long division from elementary school, okay, you would do 8 or 6 goes into 8 one time. You would do 1 times 6 is 6, and then you would subtract, and then you would bring down the next number, okay? So then you do 6 goes into 22 3 times. That gives me 18. Subtract, and I get 4, and then you would bring down the next term, and then you'd make 6 go into 47, which will go in 7 times, and we have 5. Now, when you first did this, they taught you how to do this little R for remainder 5, okay? Was how they taught. Now then, there was an in-between that happened, okay? Some of y'all don't remember this one, okay? But it was when they taught you that fractions also meant division, okay? And it was that you could do 5/6, because you could technically still try to do 5 divided by 6 in its fraction format. Now, the method that you did after this was you put in a decimal point and a 0, and you kept going. This, though, is the style that we're fixing to use, okay? So when we do polynomial long division, it's going to look very much the same. Now, when we do the division here, you do have to start with the biggest powers, okay? And so this is the problem coming straight out of the PowerPoint, but I am going ahead and putting it into order from highest to lowest. Now, if they skip a term, so if they went straight from x cubed to x, you need to put a 0 in here for this. Okay, so we've got here. Now, the way we do this, x times what gives me 2x cubed? Give me 2x squared. Okay, so now we're going to do this times both of these. So 2x squared times x is going to be 2x cubed. 2x squared times this is going to be minus 6x squared. I'm going to put my subtract and out here. 2x cubed minus 2x cubed, those are going to go away. -3 minus a negative, guys, that's going to turn into plus. So -3 plus 6 is 3x squared, and then we're going to bring down the next term. X times what gives me 3x squared? It's going to be 3x. So it's going to be 3x times x is 3x squared. 3x times -3 is -9x. Subtract. Again, 3x squared minus 3x squared cancels off. -11 minus a negative is going to be plus. So it's -11 plus 9 is -2x. And then I'm going to drop the next term. X times what? That's going to be -2 minus 2x plus 6. Subtract. Again, negative minus. It's going to be away. 7 minus 6 is 1. So the way we end this is we do plus 1 over x minus 3. So we take the remainder that was left over down here, and we put it over x minus 3. Okay, so this is our answer. Now, one of the things that happens with this, though, is if you are dividing by what we have here, like x minus 3, it's x plus or minus a number. You can do what's called synthetic division, okay? Synthetic division is going to take this whole problem and shrink it down, okay? Now, I'm going to write down the answer that we had to this problem, and then I'm going to show you how to do this problem with synthetic division, okay? So again, our problem was 2x cubed minus 3x squared minus 11x plus 7, okay? And we were dividing this by x minus 3, okay? This is the problem that we were doing. Now, here's the way synthetic works. There it goes. Wait a second. We're going to do a box corner over here. Now, beside this box corner, the only thing I need are the coefficients, so I just need the numbers part of this, okay? And I do need them to go in descending order. So this was x cubed, x squared, x, and that is number, not hashtag, okay? Everybody wants to say it's number, not, it's hashtag, but it's number, not hashtag, okay? Now, what goes over here in the box is the opposite of this back number. So instead of putting minus 3, we're going to put plus 3 or positive 3 over here in this one. Now, I need you to skip a line and draw a line, okay? And now we're going to get this lovely shindig started. The very first step you do is you're going to drop this first number down, okay? Now then, the next step is you're going to take this number that's in the box and you're going to multiply it with the number that's right here, and it's going to go up into this next spot. So 3 times 2 is 6, okay? And then you're going to add these two numbers together. And now we're going to repeat. 3 times 3, so we're going to the next spot over. To fill in this next spot is going to be 9. So negative 11 plus 9 is going to be negative 2. Repeat again. 3 times negative 2 to fill in this spot is negative 6. Add, and you get 1. Okay. Now, remember that we had this was x cubed, x squared, x, and the number. When you come down, this is your answer line, and every single one of these is going to drop a power. So if this is x cubed, this is x squared. X squared is going to turn into x. X is going to turn into the number, and the number is going to turn into the remainder. So we have 2x squared plus 3x minus 2. And again, in order to do the remainder, you put it over the original dividing thing. Now I'm going to move this document up. Guys, this is the answer that I had written down before, okay, when we had done the other math. This is the exact same answer, okay? So what this now does is it takes that whole big long division problem that we had and shrinks it to something that's this big. Now, again, the only rule is, okay, what you're dividing by. Okay, so when they say like divide by, I think they use the letter C, it has to look like this, either x plus some number or x minus some number. If this is x squared, you cannot do this with synthetic division. Okay, synthetic division is super nice and short, but if it's x squared, x cubed, anything like that, you cannot. 2x plus 3. You can't do that, okay? It's got to be x plus or minus. Oh, yeah. Don't let them do that little trick with the little flip-flopping them. Rewrite that little bugger. Yeah, rewrite that little bugger the other direction. Don't let them switch that out on you, okay? So now, Another example problem that I had was x cubed minus 7x minus 6, and they wanted us to divide this by x plus 2. Now, the reason that I like doing this one is, guys, they skipped x squared, okay? So if you're going to do this with synthetic, there's my x cubed. There is my 0x squared. You have to have it in there. Every power has to be represented. And then there's my number. There's my -6. Now, this one says plus 2 back here. So we're going to put -2 in the box. Are you at, so since they skipped, 0 isn't positive or negative, so you always just put the 0 in for it. Okay, so if they skip over it, I'm just showing that I recognize that it should have been there, okay, but it's not. So I'm just going to put a 0 in its spot to say there was, it's kind of like me saying, I have 3 dogs, 0 cats, 8 fish. I could leave out the statement and just say I have 3 dogs and 8 fish, but I can include, if they want me to answer cats, dogs, cats, fish, I need to say I have 0 cats. So it's the same idea when we're going through here. So again, we're going to skip a line, draw a line. We're going to drop that first one in, and we're going to start. So -2 times 1 is -2. Add. And again, we're going to multiply. So -2 times -2 is going to be 4. And then we're going to add. It's going to be -3. -2 times -3 is going to be 6. We're going to add. And that gives me a 0. Again, drop a power when we come down. So x cubed comes down to x squared. X squared comes down to x. X comes down to number. And number comes down to remainder. Guys, this one doesn't have a remainder. This is the same thing that happens in regular division. You can do division where stuff divides in pretty with nothing left over, okay? Think like 225 divided by 5. It's going to go in there pretty. I don't have to have a remainder. So this would be x squared minus 2x minus 3. There's my answer. Okay, so if there's a remainder, then I just write it. Now, sometimes the question comes up, what if I have a negative? Okay, so for example, what if this came out to be a -2? I'm still going to put plus, and then I'm just going to put the -2 up on the top. So if you have a negative remainder, you still just put plus and let the negative get handled up in the top end. Okay, so when they do that. Now, next thing is what's called the remainder theorem. The remainder theorem is really neat, okay? And I'm going to put the example up here so that you understand where I'm pulling. Okay, what the remainder theorem lets me do is instead of me taking -4 and plugging -4 into here and having to do okay, instead of me plugging this in, what we can do instead is I can put -4. Now notice, guys, they're asking me to do f of -4. This is not like what we just saw where it said divide by x plus 4, x minus 4. This is, they're just handing me a number. I'm going to put that number straight in here in the box. And then we're going to do synthetic division. Okay. Multiply is going to be -12. Add is going to be -8. Multiply is going to be 32. Add is going to be 27. Multiply 27 and 27, 54, 108. Okay. This number right here at the back, that is my answer. Okay, so when you run this synthetic division through, whatever this number is back here at the back, that is the same number. Now, I'm going to show you the check for this. Okay, I'm going to get rid of my synthetic down here. And I'm going to actually plug in and show you the check for this. just so that you see that this works. Okay, 4 and 4 is 64 and 4 is, so this is 3 times negative 64 plus 4 times 16 plus 20 plus 3. This is negative 192 plus 64 plus 23, 192 plus 87. Guys, that's negative 105. This is the same answer I got here. But I don't know about y'all, but I'm a whole lot faster at the little box corner, multiply, add, multiply, add, multiply, add, multiply, add, than I am at having to do all of this stuff, okay? So what that now gives me is an option that if they say, find f of 3, 3 goes straight in the box, okay? So this is the only thing that you're gonna have to be really cautious of is when they say a division problem, like divide this by, and they give you x minus 3, this is where you do opposite into the box. If they ask you to do something like this, this number goes straight into the box, okay? So make sure you're being careful of that. Now, the other theorem that comes out of this is what's called the factor theorem, okay? And guys, here's the idea. When we ask for, say, factors of 12, okay, everybody says it's 1 and 12 and 2 and 6 and 3 and 4. And the question is, why are those factors? Well, it's because when I do 12 divided by 2, it divides in evenly with no remainder. That's what it means to be a factor, is that there's nothing left over, okay? Now, I can do 12 divided by 5. It's just not a factor because I'm going to get a decimal thing. I'm going to get 2.4 or whatever else. It's not a factor. So when we talk about factors, those are things that divide in cleanly or evenly as this is processing through, okay? So when we talk about factor theorem, it works two ways. One is, if you tell me x plus 3 is a factor, when I do synthetic division, I better get 0 back here in this bottom corner. If this is a factor, when I do this, I better get 0, okay? Otherwise, it wasn't a factor. I had leftover, okay? Now, the other thing is, if they don't tell me that this is a factor, but I run something through and I get 0 right here, I just figured out what a factor is. I can backtrack this up to here and figure out what that factor must have been, okay? So the last example that they ask us to do is to solve an equation given that we have a 0, okay? And so they give me 15x cubed plus 14x squared minus 3x minus 2. And they tell me -1 is a 0. Now, this is a 0. That is code for factor, okay? That is code for factor. Now, the difference here is the factor is going to be that opposite version. So if -1 is the 0, this is the number that would have been in the box corner, okay? The actual factor, quote unquote, is going to be this x plus 1. It's going to be that opposite of it. Now, we're going to go ahead and put -1 in the box. So I've got 15, 14, -3, and -2. Okay, so running through it. Now, there is no shocker here that I got a 0. Okay, they told me it was a factor. It dadgum better divide in cleanly with nothing left over. Okay, now the concept here is, because this was x cubed, this is x squared x, and our number remainder left over. Okay, at this point, sorry, it went away for a second. It's back. At this point, guys, we can solve this because it's quadratic. You can push this into a quadratic formula. You can factor this. Anything you need to do to find the other two, okay? The concept is I went from a cubic, I don't know how to do this, down to a quadratic that I do, okay? So you can either quadratic formula. Now, this one will factor, okay? It'll go to 5x minus 2 and 3x plus 1. Okay, those are the factors. And then again, we can set those equal to 0. And then our other one is 3x plus 1. I'm over here kind of close to my stuff. Okay, so I would have this answer, and the -1 that I had up here, okay? The concept here is that you are taking a higher polynomial, like an x cubed polynomial, and getting something that will bring it down to an x squared so that you can then do a quadratic formula or factoring or something like that, okay? So that is the end of 3.3. I appreciate everybody, getting on. Like I said, I'm going to post this up into Canvas. So if you missed something, if you've got questions, if you think of something after the fact, please, please, please email me. Do an Ask My Instructor, any of that kind of stuff. That will, any of those things that you need to do to ask questions, get help, do anything like that. Again, you've got other videos available to you through My Math Lab that you can also look at, YouTube, anything like that. I am planning on doing another one of these on Friday. I may have to bump that one up to about 4 o'clock, but on sections 3, 4, and 3.5, so that should be a slightly shorter video or a slightly shorter session. But hopefully, and again, I'm going to post these into both sections that I have on Canvas, okay? So you should be able to access this. It'll be under the modules. I may have to make another module that's like the Zoom session videos, or I may just tack it up under like chapter 3 stuff or something like that, but I'll have it labeled appropriately. So hopefully you got something out of this tonight. Stay healthy, stay safe. I know quarantine's great. But hopefully everybody's still, kind of tracking with us. And for right now, I'm still planning on doing tests when we get back into class, into sessions. If that changes, I will make sure to communicate that as best I can. So y'all have a great rest of your evening, okay? Bye.